So in the previous video that I said that this extremal number is n mod half plus little 1 times n to the 5 over 3, and which was actually proved by Brady in 1996, which is not a trivial statement or comes from Kobayashi-Turan, which is different. So now we want to prove this Kolla-Ronya-Szabo theorem that if we have a complete bipartite graph which is very asymmetric, so t is much bigger than s, then we know the asymptotic of extremal number of KST. So we already know upper bound, which comes from Kobayashi-Turan, and now we want to prove the lower bound. So we want to construct a graph which does not contain KST and has at least this many number of edges. So before, in this proof of extremal number of k to 2, we first take n and then we choose p accordingly, so that the p square minus 1 in this case is roughly n but slightly less, so that we later might have to add isolated vertices with to make it exactly n vertex graph. But because of the existence of prime between any two number which is not too far apart, it's a minor point. Changing n with the p square minus 1 over there was just a minor point, which is not so important. So we might as well just take a prime p first, and we just assume n to be p to the s with our choice of s. So this will just make only minor difference. So now we want to construct a graph with this many edges having no KST. So for that we consider the following map, which sends field with k to the s elements to field with k elements, which is this. So remember that this is actually a cyclic group. If you forget the origin, then this is cyclic group in terms of multiplication, meaning that there is some element there. You can find x, so that the x squared, x cubed, and x to the p minus 1 minus 1, which is 1, and x to the p to the x, which is x. So this is everything here except the 0. Then, from here you can actually, conclude that if you take any element here, let's change this with some say s to avoid the confusion with this x. So you take anything here, and you apply this, then n of x always satisfy that if you take a p minus 1's power, then it's a unit. So from that you can actually easily see that this map always maps the number into f to the p, so which is number between 1 and p minus 1, or maybe 0 if the original one was 0. So we consider norm graph G with vertex set being this field and edge set being I mean, we add the edge between A and B if their sum has norm 1. Then this defines the graph. We specify the vertices and we specify how we were going to add the edges. So now we want to show that it has this many edges and it doesn't contain KST. So let's first prove that it has desired number of edges. So again, as we mentioned before, this multiplicative group is a cyclic group of order p to the s minus 1. So we can find s where all of these numbers. Yeah, maybe I shouldn't have used s here because it's confusing with this s. Sorry. So let's use something as a to the p to the s minus 1 are all different, and we have this. Then if you consider this n of a, you can actually, check that this satisfies this multiplicative, property. You take norm of AB is same as norm of A times norm of B. So from that, you take the norm of these numbers, then you get, all. So these are, each of them are in FP. And then these are, you take, this is some number in FP, and then you square and cube and so on. Then you can easily see that, this is some number which is not 1. And these all take, again, it's a cyclic. So the cycle repeats. From that, here we also know that this is some number in FP which is not 1. Because if this was to be 1, that means this cannot be entire thing. So it's not difficult to actually show that. And then this norm actually takes the, if you write these down, then that's a periodic sequence, which, all the p-1 numbers in FP, which is non-zero, will come out. So from that, what you can conclude is that exactly the, number of x whose norm is exactly 1 is p-1. You just divide by p-1. Because you take this generator, and this generates, again, every element in, every p to the s minus 1 elements in f to the ps here. And if, say, this was, norm of A was, say, 2, then this is norm of A is 2 squared, and this is 2 cubed, and so on to the 2 to the p to the s minus 1 in FP. And here, every number appears in the same frequency. Every number between 1 and p-1 appears in the same frequency. So exactly 1 of p-1's portion of them are 1. So as some vertices, again, might have loops. So we delete them. then we have that the degree of every vertex is at least, this number -1, this 1 comes from deleting loop. We delete the loop if the A and A there is an edge, meaning that the norm of 2A is 1. So we have, this P to the S minus 1, which is N to the 1 minus 1 over S. So this is the degree. So that means, you have by the degree sum formula, the number of edges by half times N to the 2 minus 1 over S. So this proves the claim. Now we want to show that this does not contain KST. So for that, let's use this. We are going to use this theorem from algebra. Let that be any field, and AI, J, and P are all in the element of, P, I are all in the field. Such that Aij is different from Ai prime J for all I and I prime which are different. So these numbers are given, then we consider the systems of equations these systems of equation. You introduce the variable x1 to xs, and you multiply them. You subtract the aij and then you multiply. You multiply in a way that the first, coordinates are all same, then you multiply together. Then this system of equation has most S prime solutions, S factorial solutions in F to the S. So that's one theorem in algebra. Just to we are not going to prove this theorem, but just to give you some feeling, if these B1 to Bs were all 0, then, how many solutions are there? So one of the, x1, so x1 should be one of these numbers, a11, a21, as1. You choose one of them. And here, because of this condition, these are all distinct. So there are S choices for x1. Once you make that choice, now this is 0, then x2 has to be one of these numbers. Otherwise, if x2 is not one of this number, then however you choose the last, one of these equation must be non-zero. One of these term must be non-zero, so you fail to satisfy the equation. So x2 should be one of these. So let's say this. Then on the remaining thing, x3 you have a s minus 2 choice. x4 you have s minus 3 choice, and so on. So you multiply them, then you get, s is actually s factorial solution. So this says that even for non-zero b, the number of solution is m mod s prime. So we assume this theorem. Then now we prove that G does not contain KST. So for that, again, we want it to, count the number of common neighbors of the given vertices. Consider distinct points y1 to ys in f to the ps. And we want to estimate the number of common neighbors of this. So for each I between 1 and s, what do we have? If x is a common neighbor of all of this, then we know that x plus yi has a norm 1. But what's the norm? Norm is x plus yi to the p to the s minus 1 over p minus 1, which is same as x plus yi to the 1 plus p squared plus p to the s minus 1. This is x plus yi times x plus yi to the p times x plus yi to the p squared, and so on until x plus yi to the p to the s minus 1. Then, by the Refreshment identity, so this is called Refreshment identity in any field of characteristic P. So we need for this case. So this actually becomes, so 1 equals x plus yi, x to the p plus yi to the p, x to the ps minus 1 plus yi to the ps minus 1. So we have this for all I. Then what do we have? X plus, say, y1, xp plus y to the 1 to the p. We have this x plus y2, xp plus y2 to the p, x to the p to the s minus 1 plus y to the p to the s minus 1, and up until to s. This is 1, this is 1, this is 1. And here, let's see that these numbers are all different. Because we chose y1 to ys all different, so these are all distinct. And these are also all distinct because if yi to the p equals yj to the p, then we know that yi equals yj in this field. So here, these numbers satisfy, take the minus of this. Minus of this satisfy this condition. Then, if it has more than s prime plus 1 solutions, meaning that this many x's satisfies this, then for each x, say x1 to xs prime plus 1 are the solution. No, let's not write this way. then okay, each of them gives, let's say, x1 comma x2 comma xs, which is x comma x to the p comma x to the p to the s minus 1. So for each solution, for each solution we compute this and then we consider this tuple. This tuple satisfy x1, satisfy the same equation here with this being x2 and this being x1 and this being xs. So we get n from the same logic that if x and x prime are different, then this and x prime comma x prime to the p comma x prime to the p to the s minus 1 are all different. These two are different if x and x prime are different. So we get s factorial plus 1 distinct solutions to this system's equation where aij is minus yi here. These are the ones. Then this is contradiction to the previous theorem. So it has at most s prime, s factorial solutions in X. Hence, G does not contain Ks s prime x factorial plus 1, so no KST as well. So this proves that this construction gives a graph containing no KST and having some constant times this many edges. So this is pretty much, pretty much almost all we know. We don't even know the extremal number for K44. It's not really known. Good lower bound for this is not known. And when t is not too big, also we don't know whether there is a good lower bound on the extremal number.